In this lesson, we're going to be finding unit vectors. We're going to be writing vectors as linear combinations of unit vectors, and we're going to find direction angle of vectors. So in many applications of vectors, it's going to be useful to find a unit vector. Remember, that means a distance of 1 from the origin that has the same direction as a given non-zero vector v. So here's a formula that we're going to use. We're going to divide the components of vector v by the length of vector v. And that's going to actually give us a unit vector, a vector with length 1. So let's kind of see what it looks like in an example, and then graphically we'll confirm. Okay, so we're on page 570, and I'm doing problem 50. Again, it's always important to look at the directions. So I'm going to get to that page so you can see those directions. So page 570, problem 50. It all gets jumbled when we do so many different things. Okay, problem 50 is right here. So it says find a unit vector in the direction of the given vector. And then we're going to verify that the result does have a distance or length or magnitude of 1. Okay. So we're going to look at vector v in component form -2, 2. We want to find a unit vector in the same direction. I might start with a little graph over here. Okay, if we were to plot vector v in component form that has components -2, 2, if I went left 2 and up 2, left 2 and up 2, well, I think it's quite obvious that that distance of that magnitude of that vector is not 1. It's definitely more than 1, because if you're going left 2 and up 2 and you use Pythagorean theorem to find that distance right there, or the distance formula, whichever, that's the same, that's definitely more than a length of 1. So what we're looking for is, how far do I go from the origin on this same vector? How far do I go to until I have to stop because I have a length of 1? So it's probably going to be somewhere, I don't know, about right here, maybe. That distance, that magnitude would be 1. So what we want are the coordinates, okay, of this point right here. And that's called your unit vector. So if I can figure out what the x component and the y component is at about right here, that would be the unit vector. So, and here's our formula and how we're going to do that. All right, so to get a unit vector, we want to take the components, which we already have, and divide it by the magnitude. Well, sounds like we need to find the magnitude of vector v. Again, when you see the double absolute value bars, think about the square root symbol, and let's square the x and square the y, adding those together. All right, so this would be 4 plus 4 is 8. I probably wouldn't change it to a decimal, but I probably would simplify that to 2 square root of 2. So this is the magnitude. So coming back up here to this formula, I want to take the x component and the y component and both divide each of those by this distance right here, this magnitude. All right. Actually, I'm going to come back up here, I think. So I'm just going to say that bold U, which is going to be called the unit vector, is equal to, I'll do big old symbols here. I'm going to take the components of vector v, -2, 2, and I'm going to divide them each by, what is it, 2 square root of 2? All right, so let's break these apart. What is -2 divided by 2 radical 2, comma, what's +2 divided by 2 radical 2? Okay, we're trying to find a unit vector. The 2's divide out, so it looks like I'm going to have -1 over radical 2. No, we don't have to rationalize, and it looks like we're going to have 1 over radical 2. So first things first, let me just make sure that I've got the right positive negative sign. So if I were to plot this vector from the origin and go left 1 divided by square root of 2, and then up 1 divided by square root of 2, it looks like I'm at least in the right location. All right, so this would be called a unit vector. Now, how do we verify? Well, let's find the magnitude of this unit vector. It should be 1, because a unit vector means a magnitude of 1. So I'm going to put over here, I'm going to verify. So the magnitude of vector u should give us 1. So remember, it's the square root. And we square each of these components and add them together. And then square root. And just for the sake of time, because this is going to be a long video, there's a lot of content to cover. If you did this on your calculator using all the right templates and everything, you will get 1. So we just found a unit vector that has the same direction as the given vector v. So if I were to think about where these components are, they should put me about right there, and that distance would be 1. So part of our work today is going to involve using this formula right here. Okay, so this next bit of information is a lot. I'll kind of let you know. I'm going to kind of get the information out to you, and then in some examples that we're going to be doing, we're going to use this information. All right, hang on. The unit vectors 1, 0, and 0, 1 are called the standard unit vectors. So standard unit vectors, okay, and are denoted by the lowercase letters I and J. So I want to get a visual. So let's look at the standard unit I vector. So if I come over here, if I were to plot 1, 0, remember this notation means I start at the origin. Let me plot 1, 0. So 1, 0 would be right here. I'd stop, connect, put my arrow. Okay, this is the horizontal component. The horizontal component. You can see that it is it has a length of 1, and it falls right on the x-axis. The J standard unit vector would have the components 0, 1. So this is lowercase I back here. So lowercase j would be 0, 1. So 0, 1 would be right here. So this is the standard unit vector j. So I is horizontal and j is vertical. Okay, and they each have these components. Whew. All right, so what do we do with that? Well, when we get to some examples, we'll be using that information as well. All right, continuing. These vectors can be used to represent any vector as follows. So let's say we have another vector, and maybe, you know, they're not standard unit vectors, but it's just some vector like maybe we had up here. Okay, so these standard unit vectors can be used to represent vector v as follows. So vector v, having components v sub 1, v sub 2, we can take the v sub 1 component and multiply, because remember, v sub 1 means how we travel left or right. Remember, the horizontal component standard unit vector is I. So if I take v sub 1 and multiply it by, if you will, 1, 0, add it to the second component, v sub 2 of my vector, and multiply it by the vertical component, because remember, v sub 2 tells us how far to go up or down vertically. Then we can change this component form, 1, 0 to I, plus we can change this component form to j, and we have what we call a linear combination. So that's called a linear combination. It's just a different version, if you will. It's just a different version of a vector. Okay, so hold that thought for a minute. Let's move on. We'll be using this information in some examples, and it'll become more clear, I think. All right, so the scalars v sub 1 and v sub 2, these components are called the horizontal and vertical components of v respectively. And so this is just more information about what we just did here. The vector sum would be this linear combination, and it's a linear combinations of the vectors I and j. So any vector in the plane can be written as a linear combination of the standard unit vectors I and j. So for just a real quick example, let's say I had vector w, and its components were -3, +2. How do I write this vector as a linear combination of I and j? Well, it's as simple as saying this is equivalent to, take -3, multiply it by I, take 2, and we're going to do a plus 2 times j. So when we come out of the vector component form and change to a linear combination, we take each of the components, so this would be w sub 1 and w sub 2, but we multiply each of them by I and j respectively, and we put the plus sign, no comma in here. So these two formats are equivalent. We should be able to flow from this component form to this linear combination form, and then vice versa. So they mean the same thing. All right, so let's do an example in the textbook. Let's do page 570. And we're going to do number 57. Okay, so let me get the book in front of us. Let's see what it says. Where's 57? There it is. Okay. So we got a lot of information. We got unit vectors, how to find them with a formula. We have the idea of linear combinations being an alternate way to represent the component form. Okay, let's do some examples with all this information. Okay. Maybe not all at the same time, but all right, we're going to do 57. So it says, find the vector v. Okay, so find the vector v means I need the components, okay, that has this magnitude. So all I know is that the distance of this vector that starts at the origin is 10, but what are the x and y components? Okay, so find the vector v with the given magnitude and the same direction as u. Okay, so u is another vector, maybe not a unit vector, probably isn't, because when you look at vector u, when you move left 3 and up 4 and connect, that's not a distance of 1. So we've got vector u that's not a unit vector, and we've got the length of vector v, but we want its components that give us that length. And you might see right here in my book where I have written in an alternate form of vector u in linear combination form is to take -3, multiply by I, and then add 4 times j. Just nice to know, how to flow in and out of those. Okay, so let's get back to our example. We've got to find these components, okay, of vector v that's in the same direction as u. So actually what we're going to use to accomplish that objective is the formula that we found way back up here. Let me get my notes here in front of me. Okay. Okay, now in this sense, u, and not for my example, this u right here is going to represent the unit vector we found up top, that formula. It's vector v divided by the magnitude of v. Okay, so in 57, this is the given information. All right, so what we're interested in finding is the components of vector v. So we're really interested in finding the numerator here. So I'm going to say, let's change this form. Let's actually, to get vector v by itself, let's multiply both sides of this equation by the magnitude of v. So I'm going to keep v over here. I'm going to say vector v's components are actually equal to the unit vector u, if I could find it, times multiplied by the magnitude of vector v. So I've got 10. 10's going to go here, but I need a unit vector for this vector u that's given here. So this is not a unit vector. I need to make it a unit vector. So how do we make u a unit vector? Well, we find its magnitude and we divide each of these components by that magnitude. And once we get that unit vector, we just multiply by 10. Let's write a note to ourselves. Find a unit vector of u. Then multiply by the magnitude of v. So we got to find a unit vector because that's where this formula comes from. So first things first, find a unit vector. All right, so that means I've got to find the magnitude of vector u. Here's vector u, square root. So how long is this vector? 9, 16, 25. We can do all those computations. I'm going to go kind of quick because it's going to be a long video. This is 5. All right, so the magnitude of vector u is 5. So I need to take -3 divided by 5 and 4 and divide it by 5, and that will be my unit vector. So I'm going to come up over here, write myself a note. Unit vector of vector u equals -3 divided by the magnitude. So I'm really using this version right here. It's just that I have u here and u here. And what, 4/5? How do I know that's a unit vector? I could find the magnitude of this vector right here, and it should give me 1. Okay, well, we're not done. Remember, we're trying to find the components of v. So now all we have to do is take vector u and multiply it by 10. Okay, so v is equal to, and I'll put the magnitude up front maybe, 10 times -3/5 and 4/5. And I'm trying to save room for another example. So 10 times, that'd be -30/5, so that would be -6. And 10 times for 40/5, which would be 8. Right. So there, we've got an answer. This is the component form of v. So remember what we did. We found a unit vector for this vector u by dividing by its magnitude and then multiplying by 10. And just a reminder, the linear combination alternate notation for this vector is -6i plus 8j. All right. See if I can squeeze another one in here. 61. Let's see what 61 gives us. Where is 61? Here it is. Same directions. Okay, we got the magnitude. But now vector u is written in this linear combination form. So, but that's okay. I know its components are 3, 4. So that's probably how I'll record it. Less writing. 61. The magnitude of vector v that we want its components for is 7. And vector u is 3i plus 4j, but that's as easy as saying 3, 4. So we know that this would not be a unit vector if you plotted it. So let's make this a unit vector. So let's find its magnitude. I believe that's going to be 5 as well. So the magnitude of vector u is 5. Okay, so we'll come over here. So what's the unit vector of u? Take each of unit vector u's components and divide by 5. So that's going to be 3/5 and 4/5. Okay, and so vector v's components will be the magnitude I want, 7, times each of vector u's components. So it looks like 21/5 and 28/5. Okay, and if you wanted to verify that this magnitude was 7, you could just do the square root of the squares, the sum of the squares of each of these, and we should get 7 if we wanted to, you know, do a little check on that. Hang on, still have more. This is a lengthy unit, okay? Let's turn it over. Oh, these might be easier. Ooh, we got the harder ones out of the way maybe. Find the component vector, then rewrite with I and j, okay? So I have chosen a few problems. So we're going to do 63 in the book. So these are the directions I extracted from the book for problems 63, 67, and 69. So, and this is the given information. This is our initial point, and this is our terminal point. Notice that they're parentheses. So this vector that's determined by this initial point and terminal point is not in component form because we don't start at the origin. So to find the component form, this takes us back to a previous lesson. Do we want to give it a certain name? We'll just call it V. Okay, just to remind ourselves, we start with the terminal point, subtract the x's. So 4 minus negative 3 is 7. Start with the terminal point, subtract the y's. 5 minus 1 is 4. So boom, we found the component vector. All right, so rewrite with I and j. Oh, easy enough. 7i plus 4j. Done. Oh, I'm even going to do 65 too. So here's 65. Initial point. Why am I doing so many of these? Terminal point. We'll call it vector V also. So initial, terminal, subtract the x's. 0 minus negative 6 is 6, and 1 minus 4 is negative 3. And to rewrite with I and j is simple as 6i minus 3j. Okay, we're going to change gears. We're going to do 67, which has different directions. That's right. All right, so combine the component vector, then rewrite with I and j. And then I probably needed to have some different directions for 67, but let's look at what it says here without my writing it all down. We're going to do 67 and 69. It says find the component form. Oh yeah. So same directions. And sketch the specified vector up. No, we're not doing that. We are not going to sketch geometrically. So we're going to find the component form of V, where U is 2i minus j and W is I plus 2j. All right, so let me get that down. So on 67, we're supposed to find the component form of V, and the problem is V equals 3/2 U. Okay, but previously in the directions, it told us that U was the vector 2i minus j, and in case we need it, W is I plus 2j. All right, so we're supposed to find the vector components of V. All right, well, first of all, V is equal to 3/2 U. What's U? 2i minus j. Well, I'm going to multiply 3/2 into 2i minus j, and then convert back to component form. So 3/2 times 2 would be 3i minus 3/2 j. That's it. So vector V's components with the appropriate notation is 3, negative 3/2. Well, that was relatively painless. Okay, let's do 69. Using this same given information, 69's problem is V equals U plus 2W. All right, so vector V, remember we want the components, but we first have to tackle adding U plus 2W. So U is 2i minus j plus, I want to double W. So 2 times I, so plus 2i plus 2 times 2j, which is 4j. All right, let's collect here. So 2i and 2i is 4i, and minus j and 4j is plus 3j. So vector V's components are 4 and 3. Okay, a lot of stuff to do. Okay, hang in there. All right, consider vector V that's in AI plus BJ form. Well, A is, in this example, would be 4, and B would be 3, whatever, the components. Then the direction angle Measured from counterclockwise of the vector. We wanted to know if we had a vector over here, measured from standard position, what is this angle? Okay, I can find the angle of the direction, not the slope, but the angle from standard position. I can find it by using this formula. I can find the angle called theta by using tangent of theta equals V sub 2, or B, divided by A. Now, of course, I want to find the angle, so that's going to mean we have to bring in arctan. So theta, really, what we're going to be doing is arctan of B over A. All right, so I'll kind of keep these formulas handy right here. Okay. All right, so we added another piece of information. We're looking for the direction angle measured from the counterclockwise from standard position. So, and we can find that, for example, back up here. Okay, we could find that by taking arctan of B3 and dividing by 4. And we should get some angle measured that would indicate what the angle is from the positive x-axis of that terminal point. Whew. All right, we're going to do 74. All right. And this is problem 74 straight from the book. Okay, make sure we have the vector v written down. So another way to write a vector. This is 8 times the quantity cosine of 135 degrees times I. So instead of having a number here, I've got cosine of 135 degrees, but I'm going to find that from the unit circle, plus the sine of 135 degrees, whatever that is from the unit circle, times j. And then we'll multiply that by 8. Okay, so let's look at the directions are. Okay. It says find the magnitude and direction angle of the vector v. So we've got to find the magnitude. We might want to write it in component form so we can use our formula. And then the direction angle. Well, honestly, on 74, 135 degrees is going to be the direction. So we don't even have to use arctan of b over a. Here in a minute, I think I'm going to do example 76. So I can find the magnitude quickly by squaring 8 and squaring 3 and square rooting it. But for me to find the direction angle, I'm going to have to do arctan of -3 divided by 8. So for example 74, actually the direction angle is already present in the problem, but that angle measure is not present in 76. So we have a couple of different things to tackle here. So let's find the magnitude and the direction angle of vector v. All right, well, I know the direction angle is 135 degrees. I'm done. But for me to find the magnitude, I need to know what these numbers are from the unit circle, multiply by 8, and then use my magnitude formula. So let me do a little cleanup. All right, cosine of 135 degrees, if you go to your unit circle, that should be negative square root of 2 over 2 times the I. Plus, now the sine of the y-coordinate at that same angle is positive square root of 2 over 2 times j. So I just simplified them. Let's distribute the 8 in. So that would be -4 square root of 2i plus, again, 4 square root of 2j. Okay, the component form would be -4 square root of 2 positive 4 square root of 2. Component form. And then the magnitude is what they're asking us to find. Square both components. Probably could do that without a calculator, but to save time, I think I already have it, and I get the square root of 64. That does simplify to 8 if you're using the calculator. All right, and let's do 76. All right, what are we doing? Finding the component form so I can get the magnitude, because I want to get the magnitude. 8 comma -3 absolute value, double absolute value, square root. (64 plus 9 is, what is that? 64 plus 9, 73. So done with the magnitude. Now let's find the direction angle. All right, to find the direction angle, remember component form is 8, -3. So I'm probably over here at 8, down here at -3. But remember, we want measured from counterclockwise. I want this angle measure to this vector. So that's going to be like more than 270, close to 360. Okay, to find the direction angle, arctan, B over A. What is B? -3 divided by 8. All right, make sure you're in degree mode. Do arctan, -3/8. Oop, I probably want to create a fraction. Let me check my mode. I think I'm in rate. Nope, I'm in degrees. Okay, cool. Okay, so this measure is -20, but that's not what I want. I want a positive measure, because counterclockwise means positive. So -20 would actually be when you would fall down clockwise. So let's add 360 to this -20, so it'll give us the proper name we want. So plus 360. So theta is going to be 339 degrees, 444. All right, I know the video is going long, but this last objective is not too bad, so I'm going to go ahead and continue and finish up here. All right, here we go. Another way to find the component form of a vector v, if we have its magnitude and the angle it makes with the positive x-axis, is to use the following two formulas. So it's really important you go, what do I have? What are the formulas? You know, and which one should I access? So if I've got the magnitude and the angle, I can use these formulas. All right, so we're going to do 81. So we're finding the component form. That's exactly how the directions are worded for 81. Okay, so we're given that the magnitude, the length of this vector from the origin is about 3.5. And that we're also given that its angle made with the positive x-axis is 120. So we do know 120 would be somewhere over here. So our component form should be negative positive. All right, let's get the x component. So v sub 1 equals 7/2 times the cosine for the x of 120 degrees. Well, go to your unit circle. Cosine of 120 degrees is going to be, I think, -1/2. So what we end up with is -7/4 when we multiply those two fractions. So far so good. We would travel left. Okay, v sub 2 is the magnitude times the sine of 120 degrees. So go to unit circle. The y-coordinate would be square root of 3 over 2. Multiply tops and bottoms together. We would just get 7 square root of 3 over 4. So the vector component form would be those two components. And everything looks good because if I plotted and went left and then up, I know that that would be on the 120 degree angle. And let's finish by doing 83. Okay, so the magnitude of vector v is 3 square root of 2, and the angle is going to be 150 degrees. So that's going to be a little bit larger than 120, so probably somewhere right around here. That's 150. So my components should be, again, by coincidence, another negative and a positive. Okay, so v sub 1. 3 square root of 2 times, what is the cosine of 150 degrees? Boy, that unit circle just never goes away, does it? Well, the cosine is the x-coordinate, and I want to say that's going to be negative square root of 3 over 2. All right, so let's remind ourselves how we multiply radicals. So I'm going to get 3 times negative 1, so that's negative 3, and I can multiply the 2 and 3 and get 6 and put it underneath one radical, and that's all over 2. Okay, to get the other component of vector v, we're going to take the magnitude and multiply by the sine of 150. Might as well put that over 1. Sine of 150 degrees. Well, maybe that was too soon. I will in the next line. So 3 square root of 2 over 1 times sine of 150 would be 1/2. So the second component, I can't divide anything out, so I'm going to have 3 square root of 2 over 2. All right, and because I'm at 150 degrees, I know I should have a negative v sub 1 and a positive v sub 2, and it does match up. So they're ugly, but they are correct. And then 3 square root of 2 over 2. So I know in this video there was a lot of information. So hopefully you took good notes, because maybe you can use your notes on the next test. Alrighty, thank you for your patience.